for this. So that everybody can see. All right, cool. So first of all, we're going to shift inputs. I'm going to, yeah, you guys, hey, Mark and Lucio, can you hear me? You guys can hear me, right? Yes, good. All right. But you can see, yeah, obviously you're seeing some sort of weird ass thing. Don't worry about that. We're going to move this to there. Perfect. And then hide. Hide. There we go. All right. So first thing to do is we're going to, hold on, I'm going to screen share my YouTube video. Let's see here. And share. Okay. So I wanted to make sure that you guys knew why we're talking about these things. So generative adversarial networks, from now on called GANs, because generative adversarial networks is just, it's got the exact wrong tempo to it. It's just a pain in the ass to say. So we're going to call them GANs, and that's what we're talking about here. Can do some really cool things. Like this, I'll turn off the sound here. The thing that you're watching right now, and man, a lot of you probably have seen these. A lot of these went a little viral when what's going on. And, you know, the drawing that actually is there is kind of crappy. It's a little weird, but think about what's going on. They're drawing a sketch, and the computer is filling in the rest of the image. So all they've drawn is a black line representing a mountain, and a blue line representing, hey, I want that to be sky, and oh, I want the mountain to have a little bit of top on it. And stuff. And yes, the mountain is a little bit, you know, it's all very fuzzy. It's not the greatest picture in the world, but it's a freaking picture, right? So that's pretty cool. We'll cancel that. We'll go over to here. This one I think is even neater. Oh yeah, yeah, ooh, smart. Let's do that. Boop. This one's even neater. We've got an image of a celebrity, or an image of a person, for whatever. This works on all sorts of different kinds of people. And what they're actually doing is interactively changing the hairstyles, where all they're doing is dragging things around. I want to erase the glasses, but keep the face the same. I want to change what the face looks like. I want to do all sorts of stuff. And every single time, you're not painting the image. You're basically exploring this very interesting space of somebody who looks like that and has a beard. Somebody's got hair that we want to do. We can. This is really cool. You can basically build things and explore this space in real time and change them from smiling to blonde hair to whatever you want. Man, the potential for this is really cool. Obviously, we're going to talk about how this works, but this is the neat stuff. Even this one, I love this. This one's called CelebGAN, where they've done a whole analysis. And you can see over on the side here, there is, bald, black hair, blonde hair, or whether or not they've got eyeglasses and male. And these are the images that are being generated. And these images are not images of actual people. These are images that the program is drawing that look like people, but are not actually. They're not looking up images in a database. They're creating these kind of from whole cloth, which just boggles my mind. It's just crazy. They aren't just searching a database looking for pictures of celebrities. They're making these things up. Just like that picture in the Chalk Talk announcement, every single one of those bedroom pictures was not an actual bedroom. That was something that the computer drew on its own when it was bored. And you get that. And here, you're even having some control. You can say whether or not I want a blonde or male or female or smiling or young or attractive. All sorts of stuff. So finally, one thing that's very interesting in here, there's a really cool paper called, let's go up to the tippy top, whoop, let's make this bigger too. That's as good as it's going to get. Make this smaller then. Photorealistic single image super resolution using generative adversarial network, GANs. And the results they get are super extra cool. So what they are doing when they're training this thing is that they're taking a high resolution image and they're subsampling it. They're creating an image that's quarter the resolution. Then they're asking the image to be up-resed. So this is the original image, by the way. And then all of these guys are the exact same resolution because they're the same size, right? This is standard up-resing, where you're trying to basically make up data, right? You've got a small image, you don't know what it's supposed to look like. And so if you just interpolate between the pixels as you go up, you get this. It looks fuzzy. Even though it's a higher resolution, it doesn't look good. But then you start using some generative adversarial network techniques, and all of a sudden the computer is not just filling in the data. It's not interpolating the data. It's actually going, I've seen what low resolution images look like. I've seen what high resolution images look like. Let's see if I can make this look like it should, where it's kind of deciding what should be, right? And so you get, instead of a blurry image, you get a really high resolution crisp image. And notice it's filling in frickin' detail, right? I mean, we zoom in here and it's actually, it's not exact. There's what it really should look like. This is what up-resing gives you, which is really fuzzy and everything gets out. But it's actually drawing in things. It's saying, you know, really, there should be some detail in here, and it doesn't quite match. Look, there's that starburst over here, and there's this thing here where it's got a little bit of a center, but it doesn't actually do it because it doesn't have enough information. This is what the straight ahead interpolation does. But man, oh man, it's got it. It looks a little flat on the cheeks and stuff, but well, the original image is fairly flat, but wow, this is cool. This is really neat. So that is what we're going to be talking about. This stuff was invented by this guy, Ian Goodfellow, along with his collaborators in 2015. And it's fun to read these papers because a lot of the papers are, Ian Goodfellow put this thing out there. He said, look what you can do, blorch. And since then, there are a whole bunch of papers that are going, all right, this looks really cool. How do we get it to actually work? And they aren't so much scientific papers as they are, we took this, we tried to do this, and this is what we had to get it to work. And the next person says, well, we tried what they did, and then we did this. And the next person says, well, we tried that. It's very much a conversation about how to make this stuff work right now. All right, so I'm going to stop screen sharing if I can. Let's see, I want to go back to my other window. Let's just iconify this. Yeah.
I wonder if you can do a presentation mode because we're seeing you in the corner here.
Oh, well, don't worry. I'm going to stop doing that now. I'm going to stop,
okay.
And we're just going to go back to me in the chalkboard. Yay. And let me just position this so you can actually see the chalkboard. There. Burp, burp, burp. We're fine. That's good. Okay. Yes, all recording. All right. So they moved the light. Yeah, they moved the light. Let's see if I can turn this without snapping it off. It's hot. All right. So, first of all, before we go into this, we're big caveat, as always, with Chalk Talks. I talk about stuff that I find is interesting and fascinating, and I know very little about. So, if you have any experience about this, and I say something wrong, or I just don't know what I'm saying, please chime in. Serial networks. And this is going to be an all over the map kind of thing, because I'm trying to figure out exactly how to explain it in my head. But first, the easy part is neural networks. That's the easy part. We've talked about neural networks all over the place, and I want to, before we get into this, we have to review it to make sure that we all have the same basic understanding. And we're going to go back to our old example of a digit represented by images, or a single image, and it's a small image, a 24 by 24 pixel image. And what we want a neural net to do is to determine whether or not this digit is actually the number 8. So what we're going to do is stretch this thing out. This is a very basic neural net. And we're going to stretch it out into all its pixels. And then we're going to put in these layers. We've talked about these layers before. We're going to put in a whole bunch of layers. And this is easier to draw than the circles. And we're going to connect every layer to every single pixel. You see this classic image of all these lines being drawn. And all these kind of things being drawn. And eventually this guy's there. And to each one of these guys, there's going to be a weight. There's going to be a Wij, which says this guy to that guy has a certain weight. And then also, inside this thing, there is a D, which is an offset. And this would be B sub j, because this is j, this is I. And then we're going to have more layers of this. We're going to have other layers like this. And then we're going to talk about what's inside there. And these guys are going to be connected, lots of connections. And eventually, at the end, we're going to have a 10-digit 0, 1, 2, all the way down to 9. One hot vector, and this is going to be connected. There'll be some math in here as well. So each one of these is connected. And then at the output, this thing is either going to be a 1 or a 0, or a number between 1 and 0, telling you what the probability is that the digit that the thing that you're looking at is a 0. If it's a 1, then it's probably a 0. If it's a 0, then it's not a 0. And inside each one of these is a sort of an activation unit. And what this is, we've talked about this before, is it takes the stuff that's coming in and maps it to a value that's between 0 and 1, or it maps it to some value. Well, the classic case is this sort of function that looks like this, right? Where we have a nice slope in the middle, but once you get farther away from the center or wherever you're at, you get to either a -1 or a +1, or we can shift this up and make this 0 and this 1. And this is tan h, or the sigmoid function. You'll hear that kind of thing. We're gonna talk a little bit more about this. So what happens is, at each one of these guys, there's a little thing, and there's a little math that goes on. We take all the values that you're connected up, and so there's a great big sum, and you multiply Wi sub j times the input. So whatever this value is here, we'll call that A sub I. And then we're going to put this plus B sub j, and then we'll put this whole thing, sum, into our tan h function, tan h. Oops. So that gets popped out, and the result of that is what ends up right at this point. So that point is this result. Okay, so think about what this is doing. Think about it before we go any further. It's basically looking at all the input that it has available, and then it's basically weighting the input. It's doing something where it's looking at it going, you know, for what I'm doing, for my little task, certain pixels have a higher weighting, lower weighting, and whatever. And the result of this is another number that goes between 0 and 1. So 0 and 1 in this case, instead of -1 and +1. And so you have pixels that go from 0 and 1. It's either black or white. And then you add them up and you multiply by weights and stuff, and you produce some number. But then this activation unit thingy maps back down to 0 and 1, and then it goes on. And it goes on. Eventually, there's an activation unit here that does one last try to this and maps it between 0 and 1, which is the probability of whether that number is that digit. Going fast because we wanted to. But think about this. We have a whole bunch of weights, we have offset, and we have this function that's doing the mapping. And the way this works, in just a bare bones neural network, is you take a bazillion digits that you've represented with, you've got images of, and that you have carefully crafted and labeled and said, this sucker is an 8. And so you initialize this network with random numbers. You actually choose random values of weights, random values of offsets, or maybe set the offset to 0 or whatever you want to do. And you run this thing through there, and what happens at the end is garbage, right? At the very beginning, when we give this thing its first digit that it's ever seen, it runs through here and goes and spits out random numbers basically over here. But we know what it should be. This really should be a 1 there and a whole bunch of zeros. And so back in the late 90s or whatever, I can't remember the name of the guy, but there's a guy who came up with this back propagation technique. It said, hold on, I know how to solve these kind of problems if I just had math. What I'd like to do is, as I'm going through here, I'm going to calculate the derivatives of everything that happens. I'm going to figure out what would happen if I wanted a change going back the other way. Now, basically, it calculates the derivatives going forward, but because we have the derivatives, we can kind of flip them and say, what would happen if I wanted to change the other way? So as we go through, we calculate the derivatives, what would happen, and then at the end, we have a change that we want to apply. We have the results that popped out because of 8 garbage results, but we know what they want to be. So we can subtract the difference between these things and say, well, hold on, I want to change this network, and I want to push this change all the way back through the network. And so you do that. You say, I'm going to take this, take the change, and push it through here, which will cause things to change here. All these W's and stuff that are associated with this will change ever so slightly. And then you push it back further. And all these W's change ever so slightly. And then you don't change the input because you can't change the input. But eventually you change all the W's and V's so that it gets ever so slightly better at recognizing that 8. Then you throw the next image at it, do it again, wash it back and forth. The sort of forward propagation, figure out what the result is, push the results back. And eventually, if you do this enough, and you do it in a nice way, all the W's and the V's get really good at recognizing digits. All right, that's base neural networks. Now, one of the cool things about this, and the one way of thinking about this that I love to think about is, this is a form of compression. Right? This is a way of compressing data. So right now, we're actually, it might be not compression because we might actually use a lot of data. But think about what we've got. We have a database of 64,000 digits that we've classified. And now we've trained this thing to be 99, a good base level neural network like this can be around 96% accurate. You have to go to convolutional neural nets to get higher accuracy. But a base neural network like this can be 96% accurate about recognizing digits. So you have a database of 64,000 digits that when you throw it through here, will actually tell you what digit popped out. That's pretty cool. And in fact, we don't have 64,000 W's. The number of W's here are typically around 800 or so. You might have a couple of layers of that. And so you are taking all this information. What does this 64,000 entry database look like? And you're compressing it down into this thing that kind of now recognizes the stuff. It's a neat form of compression. But also, it's doing something interesting. This is one of the things that I wanted to talk a little bit about. And this is one of my Achilles heels, by the way, is probability. I'm not all that good at probability and statistics, but there's a lot of probability in this thing. And when we get to generative adversarial neural networks, it starts out with probability. This is the probability that the number is a 0 given the input. Now we'll say Z is the input here, right? A little notation saying that this is the number, the digit 0, given this input. And we're going to take a little side trip to maximum likelihood estimation. Before we talk about generative adversarial networks. So, maximum, and again, they hide the fact that this is all about probability by using the word likelihood. Say I have a whole bunch of penguins. And I'm actually making this up, or I'm not making this thing up. This is from a Wikipedia article about penguin or maximum likelihood. Let me say I have a whole bunch of penguins, and penguins occur in a certain height ratio, or the heights. This certain species of penguins ranges from 1 foot to 1 foot 3 inches. Small little penguins. But we only know a certain sampling of this. We want to actually know the exact probability of having a penguin. So if we started choosing penguins and actually holding up a ruler to the penguin, we started saying, all right, that penguin is at 1 foot 1 inch, or 1.1 feet. And the next penguin is over here, there. And there's a tall penguin over here, and there happens to be a penguin over here. Oh, there's a very short penguin here. All of a sudden, you're going to start building up this sort of marking of where penguins are, right? You get a lot of penguins over here. That can be represented as a probability density function. You know, if I choose a penguin and I don't know what I'm going to get, I could have probably a normal distribution, a Gaussian normal distribution, centered at a certain point, let's say 1.2, with a certain radius. You know, you specify the standard deviation of the Gaussian distribution specifies how far off that distribution lies. So by looking at a bunch of penguins, I can actually get a continuous probability density function from this. And maximum likelihood estimation is the whole realm of taking individual samples like this and fitting a curve like that that accurately or fairly accurately represents what that distribution is.
Isn't that normally just called the expected value of the PDF?
Yeah, that is the expected value of the, Ron said, it's the expected value of the PDF. But maximum likelihood, the field of maximum likelihood is how you calculate this for a whole bunch of different kinds of data. Because we're going to get into that. Think about this in terms of multi-dimensional data. Say that I've got, looking at my penguins now, I now have a probability density function for the height of a penguin. So if I wanted to create a penguin, a random penguin, I know that to do it correctly, I would sample from this probability density function. I probably wouldn't create a penguin that tall. That would be a bad penguin. In fact, a penguin this tall is a totally non-existent penguin. But think about that. In terms of, if I didn't know anything about penguins, I wouldn't know. I know that there wouldn't be any negative height penguins, but I wouldn't know anything about the fact that penguins occur in this range. This little probability density function tells me that penguins live out here, and I don't get a penguin that's 10 meters tall. Likewise, what about the number of eyes? If I'm going to create a penguin, the number of eyes, well, I know that I don't have 10. And in fact, if I start sampling, I get a whole bunch at 2, right? So I get a probability density function that looks like that. And number of feathers. Number of feathers, I don't even know what feathers are. But I bet there's a probability density function that's really wide. And there's some value in the middle, the expected value of the number of feathers, but the standard deviation is quite wide in that, I would guess. And all of a sudden you can start thinking about, well, if I wanted to build a penguin generator, if I had this kind of thing, then I could look up in my penguin generator for each one of the parameters of this thing. You can kind of see where I'm going with this, right? If I'm going to be generating faces or whatever, there's going to be things that tell me how to build this penguin. All right, now keep this in the back of your mind. So now we're going to go into generative adversarial networks. You need to know that.
So, Doug, before we do that,
Yeah.
In terms of just the neural networks that we talked about first,
Yeah.
and those probabilities that come out, and then what we talked about in terms of maximum likelihood, is there a specific relevant relationship there, or does that come into play when we go on to the GANs and talk?
That's an excellent question. So what Cyrus just asked is, how does this all tie together? Well, let's go into the GAN topic, and we'll just go right to that. Say we have, now instead of digits, but this could be digits, but say we have faces. And we want to build a neural network that instead of determining whether there is a face in this picture, I want to build a neural network that can actually generate this thing. It's like I was generating penguins. Then you think about it, and you go, okay, well, do I have to tell the neural network about eyes and hair and all that kind of stuff? We don't even want that. We want a neural network that can figure out what it needs to figure out in order to do this. So we start off with a probability density function that is how many dimensions? This threw me when I first started reading the radial or these GAN papers. Say I have a 256 by 256 image. There is a cloud with 256 dimensions. And I'm not going to try to draw that on the chalkboard. There's a cloud of 256 dimensions where inside each pixel, I can vary the value between 0 and 1. So there is a 256 dimensional cloud of valid pictures. Most of them are noise. But somewhere in there, and this is where the probability stuff is, there's a probability or density function, n-dimensional probability density function that chomps out a region of these pixel things, and I'm drawing it connected, but it isn't even connected. It's a weird kind of thing. It's this blob, and it's 256 dimensions. You can't even draw this kind of thing. But there's an area inside this space of all possible pictures that is valid faces.
Isn't it 256 squared?
Oh, yeah, 256 squared. Thank you very much. I forgot. Yeah, it's 256 times 256. Even better. Thank you. So there's this area inside this thing, this huge space of all possible 256 by 256 images, where you actually get a face. All right? So now our neural nets seem powerful. What we want to do is try to learn where that shape is, where that space is. Because if we could figure out where that space is, then we could browse the space, right? We could have this neural net sort of start generating faces that we've never seen. So just like when we were doing the penguin thing, we're going to start lining up penguins and measuring them. So we're going to start lining up penguins and putting them in this space of images, or well, faces now. And we're going to start teaching our thing about faces with the hopes that at the end of this, it has a good understanding of where in all these images faces lie. And now, if we know that, we can start poking around inside the space. That is one of the key concepts of this. This is where this probability density function. So if you read the first generative adversarial net, all right, the promise of deep learning is to discover rich hierarchical models, which we'll get to, that represent probability density functions over the kinds of data encountered in artificial intelligence applications, like generating faces or whatever. So that is what that sentence means. We're trying to discover these crazy ass 256 by 200 times 256 dimensional probability density function that if you are inside there, if you're near a peak in that probability density function, you're probably producing a face. Now, the trick is, you want to do this in an unsupervised way. And so, this is where the generative stuff comes into play. We know almost nothing about stuff. So we're going to actually create two networks. All right, you ready? I'm going to create two neural networks. One, and this is Goodfellow's idea. One is the generator network. And quite frankly, this is the one that we're really interested in. This is the generator network that, given an input, produces a desired result. But you can't do that by itself. We actually need a discriminator network at the same time. So there's two things going on. And what we're going to do is we're going to call this one G. And it gets some sort of input, which we'll talk about in just a moment, and spits out an image of a bedroom. So this is a bedroom, or let's call this as a bedroom. Now, it kind of looks like a typical neural net. You give it an input, it does something, you look at this and you say, well, okay, this isn't a bedroom. I want you to change how this thing works so that the next time you see something. This is the weird thing, is that will give us a way of sort of identifying bedrooms or identifying images that are bedrooms. We want to be able to create a generator that can create bedrooms, that sort of understands bedrooms even better. So Goodfellow's idea was, well, let's do this. Let's put in a plus sign here, and we'll put in here a database of bedroom images, real bedrooms. All right? And then at the end of this, we're going to have our discriminator and it's going to put out a result that this is either real or fake. So let's think about this. Neural net here, neural net here. The W's and the B's, different W's and B's. And the analogy that's going on with the generative adversarial neural network is that you're actually building on two neural nets. Let's make sure this is clear. Generator. You're building two neural nets at the same time. Because initially, both of these guys are starting out with random numbers. They're garbage. And
your input is random garbage too?
And the input is random garbage too. This thing is actually going to be random numbers. Well, we'll get to why this is in just a moment. This is the cool thing about this whole thing. This is really neat. Is that, remember in our first thing, we were sending in images of labeled digits? This thing is getting stuff. It's getting random numbers that it's going to use to create images of bedrooms. And notice the flow of errors. The images of bedrooms never reach this. It never actually sees a bedroom. By the time this thing is actually created, it will have never looked at a real bedroom. It will just know how to create bedrooms given a list of, and this is to get into actual detail, in the original paper, this is 100 random values. Got a Gaussian distribution over from 0 to 1. Blows your mind. It's like, what? This thing is going to learn how to draw bedrooms without actually seeing a bedroom. And the way that works.
So those 100 random values, so they're initialized as random values. When you talked about the neural networks before, the backpropagation, of course, doesn't go to the inputs, right? It's just going away to the network.
Yeah.
But in this case, is backpropagation actually modifying those inputs, or
Nope. And we'll see that in a moment. We got to get there. You've got a good point. What these things are, we'll talk about that in how they work, because they're going to allow us. These guys, I'm jumping ahead, but again, I don't know how to explain this. These guys are called latent variables. And the cool thing is, when this thing works, what's going to happen is you're going to start putting in random numbers, and the generator is going to generate bedroom pictures, right? Or faces. Faces are easier to deal with. And so as this thing goes and goes and goes, different values of this random number, and it's a low dimensional value, it's only 100 numbers, are going to be basically exploring that probability density space. They're going to be our keys into getting into that probability density function, right?
So the idea is that you're making a bedroom generator, which for any random inputs will give you bedroom, but for each different random set of numbers will give a unique bedroom.
Exactly. That blob of faces that I drew over here in the probability density, we need to have some way. It's a number that has 256 square dimensions. Or it's a space that has this thing. How do we navigate inside there? That's what that thing is going to become. It's going to be our navigator into the probability density function that is this generator. And as we move these values out here, the hope is that any value that's between the right normally distributed is going to produce bedrooms. We start putting values outside of those things, you're going to get whatever, who knows? You're getting outside of that probability density function. But as long as you are screwing around with these guys in an appropriate way, you're going to get a different bedroom. And the cool thing, that's the really cool thing is, that as there was one guy who works at NVIDIA noticed this, in fact, that the generator starts assigning features that it sees over and over and over again to a single number in this thing. This doesn't happen, it's not automatic, but he noticed that, hey, if I slide in between one of these values, I'm actually getting different eyebrows on my person. And so that kind of actually happens naturally, not all the time, but and there are papers on how to guide that to happen.
Is there any, so it seems to me that it's like, is that because of, if we think about principal components analysis, yes, and the kind of statistical meaning of it, is there a connection there?
That is sort of my imagination. There has to be, right? Because you've got this space, right? You've got this large dimensional space that is faces, but you've only got 100 numbers that you're using to explore. And so as these things are generated, you kind of want those 100 numbers to travel along the good bits of that space. And so it feels like a principal component analysis kind of thing. But that is an intuition. I haven't read enough papers on this to guarantee that. But that's the cool thing. Now we're not done yet, by the way. We still have to do the counterfeiter analogy. Because remember, this sucker has never seen an actual bedroom. It's becoming a bedroom generator without actually seeing it. This is the thing.
How do you do back propagation from this Boolean that comes out of the discriminator? How do you
all the way up?
But you just say, okay, well, you said false, but we're going to say it's true, and what do you have to change to make it true? It
seems like the goal of training is to eventually trick the discriminator.
Yes.
Oh, dude, you've read ahead.
Well, it'll make your discriminator better, and it'll make your, well, if you have trained data, if you have label data, then it'll make your discriminator better.
So these guys are jumping ahead. Think about what the discriminator is doing. It's doing exactly what it should be doing, right? So the analogy that you're going to hear from Goodfellow and everybody else who's done this is this guy is a forger, right? This guy's a forger, and This thing is going to be the cop who looks at the forgery or the thing. This thing is generating $20 bills, and we have a database of what $20 bills look like. So what this thing does is it says, I'm going to randomly choose between, well, randomly choose. I'm going to choose between giving you a generated image or a real image. And the discriminator is going to start looking at this going, how is this real or is this fake? And so initially, it's going to know nothing. And the backpropagation is just going to start training the discriminator. And in fact, this is usually done in a two-phase propagation, where we often train, and the papers initially, this is something that isn't quite clear. It looks like in some of the papers, training the discriminator is important. So you want to train the discriminator more so that it gets good at recognizing reals. But then they say if you overtrain it, then this thing stops working because the discriminator gets too good at recognizing fakes. And you can't actually train the generator to get any better. So there has to be this sort of balance where the discriminator initially is lousy, but the generator is for crap. And you want to make sure that these guys get good about the same level, so each one is sort of feedbacking each other.
But wouldn't the discriminator get worse over time?
The discriminator,
As the generator gets better, and you're back propagating those results back through, then you got to figure that there are going to be some generated stuff that doesn't really look real that's making it through and getting back propagated, and it's going to start getting less accurate.
You have to tighten up a threshold, like an accuracy threshold. That's like, it has to be this. The difference has to be this good before.
But it's going to start getting trained from the generated stuff, right? When you're back propagating all the way back to the generator.
It's always doing it or. It's like, are you similar to this image in the database, or this one, or that one? Right.
Right.
Iterate through that database.
this discriminator, that we do know whether this is real or fake at the end of here. So, you know, the discriminator eventually wants to get to a point where it can't tell. And it gets to a point where it should be producing pretty much, remember, this is a probability thing. So initially, it'll probably be pretty good at figuring out reals. But, you know, and probably pretty good at figuring out fakes. But eventually, we want the result of this to be a 0.5 and a 0.5, no matter whether the input is coming from here or there.
But I think that's one of the ways you can achieve that, getting back to that point, is just make the discriminator really lousy, right?
Yeah, well,
So
I think
You're done.
reading the papers, they are very lousy at the very, very beginning, but as they get better, this is where the super resolution stuff, where the generator of figuring out the actual details of stuff here, you want them to get good at the same time, because then the generator starts getting that subtle bit of, instead of producing fuzzy images that look okay, it actually starts producing sharp images that look really good. So cool. So, yeah, say,
No,
go, because no.
Well, okay, so you were talking about the generator making sharp things. A friend of mine was watching this online, was texting and asked, and I had the same idea. It was the image the thing that took the down-res image and sharpened it, and added details that didn't exist. How does it handle it temporally? And what do you have to do?
Dude, that was my first question. I was going to add. Yeah, we have to ask the author of that paper. I don't know. I haven't seen a lot of videos. So.
You might be able to do that with the different. I know that I can take several data in, but yeah, that's kind of. Anyway. That's all that was. That's why I was trying to refrain.
Yeah, no.
I'm moving back a lot.
Just start off with the generator is just generating images that are completely noisy and fuzzy. It's generating faces, right? There's no initialization of it's just random pixels, right?
Yeah.
And eventually has to get to a point where that random pixel becomes enough form to look like a face that.
But also remember that the discriminator at this point doesn't know anything. You know, it's going to see noise versus this, and it's always going to be wrong, probably. But eventually, you're going to start saying, hey, this was a real one. And so tweak the discriminator. And then this is a fake one. Okay, tweak the discriminator to get better. And it's kind of cool. Now, the backpropagation, by the way, I should go through this. So just to put some clarity on this, we'll go back to the original paper. And the algorithm is sort of helps. for a number of iterations where this is huge. These guys take a long time to train because you can imagine you've got two neural nets and they're sort of fighting against each other. And that's where the adversarial, by the way, comes into play before I start this. So the generator will get better when it can produce images that fool this. This thing gets better when it can tell whether the image, even the best image that this thing will produce, is a fake. And so because this thing is trying to get good and this thing is trying to get good at telling things, there's this adversarial kind of back and forth. And in fact, the Goodfellow spends a lot of time talking about game theory and how this actually is proven to converge given a large enough network and a large enough training data. This thing will actually work. All right, so notice what happens. So first of all, for a number of iterations, we're going to do this over and over again. For k steps, we're going to do another loop. We're going to sample a mini batch. By the way, mini batch, when I was initially doing my gate through a neural net producing a result, I was doing one sample at a time. This is sort of a stochastic gradient descent, where I send one sample, I use the results of the sample to fix the neural net, and then do another sample, and so on. But actually, they found that sometimes can produce really bumpy results. One thing will produce a large change, or a change that sort of screws up, and the next one comes around and bounces around. What you can actually do is run a whole bunch of numbers, a batch of numbers, through this thing at the same time, look at the results, and then correct based on the results of that little batch of numbers. And so instead of doing one image at a time, you do a small little mini batch at a time, and then you use the results of this to correct. So you're basically correcting in this, instead of just a single vector of corrections, you're actually getting a Jacobian of corrections. You're getting a matrix of corrections, and you're using that to go through and correct this all at the same time. And that has a smoother, more well-behaved thing. And all the really hot neural net people are doing mini batches now in order to get some better convergence rates.
Is there a curve to that mini batch? Like how it improves things? Like, you know, as you scale it, is it always better just to always use more, or do you get to this point where it starts to get worse? Or do you have any, like, I know you eventually become memory is the problem.
You're right, memory is a big deal. The nice thing about this, by the way, is just like the execution of this can be parallelized since you're doing a mini batch of things.
Yeah.
The mini batches that I've seen, I've read a couple of papers where they've said the mini batch size, and it usually ranges between 32 and 256. And that's all I know.
Now I want to see a graph of that.
Yeah, this would be, there are papers about mini batch training and stuff like that where they've gone into some more detail. So we sample a mini batch of noise. So this is Z 1 through N. And so this guy, this is Z, right? Hold Z in there. And then sample a mini batch of images, examples. X1 through Xn. So this is from the generative distribution. So that, you go through here, and this is, we generate, so this is X, right? That's X right there. So we run Z through our generator, create a whole bunch of these guys, right? Because we need this. We're going to be updating our discriminator. Update discriminator. In ascending stochastic gradient. Now I'm going to write down a little math, but it makes actually a little bit of sense. This is the parameters of the discriminator. This is D. So these are all the weights and all the biases and all the stuff that's inside there. This is the equation. So we're going through, sorry, this is n. Small font. So this log of x plus log 1 minus d, so g z, so parentheses, close parentheses. So this is the cool thing. This is the probability density function. This is the thing that we're going to be updating the discriminator by. So now, d x sub I, and by the way, the mini batch examples can come from either the bedroom or the generated thing or the real database. So this thing is saying, if this is fake, no, if this is real, we want this thing to recognize it. If it's fake because it's coming from G, based on where Z is, so this X comes from this guy, we want to minimize this. So there's, back to the original thing. All right. To learn the generator's distribution P sub G, so this is the probability distribution over the data X. We refine a parameter on input noise variables, P sub Z. So this thing is going to be generating a probability density function based on this random noise function. So we train D to maximize the probability of assigning a correct label to both the training examples and samples from G. So what we want to do is make sure that this guy, D, is assigning the correct label based on whether it came from here or from there. We want this to get good at determining whether it's fake or not. So if it's fake, it should have a high value in fake. If it's real, it should have a high value in real. We simultaneously train G to minimize that. So we want to be the opposite. So we want to make sure that this, which is our discriminator, is as good as possible, right? We want to make this perfect. And we want to make this as bad as possible. We want to make this, really, the thing is generating stuff that really fakes out the discriminator. So that is the second step in here. This is actually works out to be, it's called a min-max algorithm, where, well, this is that. Finally, we update that, then this is a for loop. And then after that, we're going to skip over here because I want to keep the rest here. So we sample a mini batch of noise, Z1 through M. And you update the generator so that there, G, we're going to change all the values in here based on the sum of all these guys, log 1 minus D, G. So this thing tries to be really good at recognizing reals from fakes. This thing tries to get as good as possible at faking the thing out. Because remember, this thing is whether or not this thing got faked out. And this is one of the key things here. This thing happens, at least in the original paper, more than this happens. There's a for loop around this. So we start training the discriminator to be a bit better than this. So we actually run this about, in the paper, it was like on the order of 5 or 10 times more than we actually run this. So the discriminator starts getting better before this thing generator can actually kick in. So initially, you're going to be generating noise, like you said. And this thing is either going to get real values or fake values. And it's going to start getting good at recognizing noise from fake. But then that is going to get fed back into here, and it's going to start changing this thing based on this, so that this gets good at not generating noise, but generating things that fool the discriminator. That's the key thing. Is that again, this neural net, which is completely separate from that neural net, never actually sees a bedroom picture. It just knows whether or not this thing got fooled or not. It gets to see whether or not that's fooled. Nothing else is created on it. What was more that? Now, there's a ton of extra stuff that goes on in here. How you build these things and how you train it. There are things like leaky rectification linear units, leaky LRUs. Instead of using tan-H, this thing is actually used a ton in these guys in order to control how they look. And there are things like using max pooling. Even think about what's going on here. We're running out of time. But think about a generator. A generator is taking 100 numbers, and producing an image, right? How do we get from here to there? Well, this is where convolutional stuff happens, but you're kind of doing what's incorrectly called deconvolution, where you're using a convolutional technique to expand this. So we have layer after layer that expands the 100 numbers into what eventually turns out to be an image like. And the thing is good. We are not going to stop with this. We're going to come back to this. We're going to talk more about generative neural networks in the coming months. But this gives you a sort of idea. It actually works. You can download a ton of different examples. TensorFlow, Theano, Lasagna, all over the place. Oh, it's so cool. It's so cool. And when it works, it is magical. Bye, all.
Thanks, Doug. All right, what does leaky mean on the ReLU?
Leaky is...
Because the ReLU is just
Leaky
max.
is...
Max. Zero.
So this
Zero
is
X.
rectilinear linear.
Yeah.
What's that? Leaky is that. So the generator is. So it has a slight slope instead of zero. So you don't,
Oh, so you don't get just stalled out with the bad gradient. So many